In the last video, we have learned how to evaluate the integral, especially contour integrals. Today, we start discussing section 43, upper bounds for moduli of contour integrals. To find the upper bound for moduli of contour integrals, we first evaluate an upper bound for uh, an integral of omega of t, that is a piecewise continuous complex valued function defined on reals, or in particular in a closed interval. So first of all, we prove this lemma to obtain the upper bounds for moduli of contour integrals. So first of all, we have to prove that this modulus of this integral is always less than or equal to this integral of modulus. So first of all, we write yes, the left hand side is a modulus. So first of all, we put that integral a to b omega of t dt, that is equal to, we put it as a complex number, say r naught e to the power I theta naught. Suppose this is a complex number, then the modulus, the left hand side represents r naught, that is the modulus of this integral. So we need to prove that this r naught is always less than or equal to this quantity. So first we write what is r naught. First of all, we write this r naught is the modulus of that integral, and we can obtain r naught from this equation by multiplying both sides by e power minus I theta. So that will be e power minus I theta naught times integral a to b omega of t dt. So this is obtained from this equation by multiplying throughout with e power minus I theta naught. So when you multiply this quantity on both sides, we will get right side will be r naught, because e power I theta naught and e power minus I theta naught reduces to 1, then the right hand side will be r naught, and left hand side takes this form. And now this theta naught is independent of this t, then we can take it into the integrals. So that is integral a to b e to the power minus I theta naught omega of t dt. Now we know that the left hand side of this equality is a real number, as this r naught is a real number. So in fact, the right hand side is also a real number. So since this is a real number, when you put real value, real part of this complex, the right hand side, that will be a real number as well. So we can take real part on both sides. The left hand side will be r naught itself, the right hand side will be this times omega of t dt. Now we observe the right hand side. We need to prove that this r naught is less than or equal to something. So we observe the right hand side, that is the real part of a complex number, that is the real part of the complex number a to b integral a to b e power minus I theta naught omega of t dt. But we know that real part of a complex number is always real part of a complex number z is always less than or equal to modulus of z, because this is the square root of x square plus y square, if z equal to x plus iy. So mod x is, or modulus of this quantity is always less than or equal to this, or real part is always less than modulus. So we can put this real part is always less than or equal to modulus of such thing, okay, modulus of this complex number. Now we write this is modulus of integral. So we write that integral as, first of all, we write this as, we put the real part of this integral first of inside, that is, we write this is integral u plus iv is defined as integral u plus I times integral v. That means if this is f, then integral f can be written as integral u plus I times integral v. What is the meaning of this? Real part of this integral f is equal to integral u. If this is a complex number, then right side is also a complex number. So first we observe that what is this quantity, then we try to obtain the upper bound for that. First of all, we write real part of an integral. Okay, real part of an integral is this. If f is equal to u plus iv, then integral f is equal to integral u plus I times integral v. So what is the real part of this integral? Real part of integral f is nothing but integral u. So that is the real part of this complex number. What is integral u? That is integral. What is u here? U is the real part of f itself. So that is in real part of f. So real part of integral f is always same as integral of real part of f. So we can write it as, this is same as integral a to b real part of e power minus I theta naught omega of t dt. Now we observe this quantity. Okay, so what we have used here is this result, real part of integral f, that is equal to integral u by definition, and integral u, this u can be replaced by integral u can be replaced by a real part of f, because f is u plus iv, so u is the real part of f. Now we observe, that's why we write this expression as integral a to b real part of this. If we take this as the our function f, complex function f, then real part of integral f can be written as integral of real part of this whole quantity. Okay, real part of this whole thing. Now we observe what is real part of e power minus I theta naught omega of t. Now we use this result, real z is always less than or equal to mod z. So real z is always less than or equal to modulus of e power minus I theta naught times omega of t. When you split this modulus of e power minus I theta naught is 1, then this is always equal to modulus of omega of t. So now we replace this quantity in the integrand of the above integral by this modulus of omega of t. Now we will get r naught is always less than or equal to integral a to b. We replace this quantity by an upper bound, that is modulus of omega of t, that is omega of t dt, that is this r naught is always less than this. What is r naught? R naught is the modulus of this integral. Okay, so modulus of integral a to b omega of t dt is always less than or, this is r naught, which is always less than or equal to integral a to b modulus omega of t dt. So this proves this lemma. Using this lemma, we will find an upper bound for contour integrals as well. Now we prove this theorem. Let's see, denote a contour of length L. We already discussed what is L. L is defined as the integral over C. This L is the length of C. That L is defined as integral over C. What we write this is dz, or you can write this as integral a to b modulus of z dash t dt, where c is defined as z of t, where a less than t less than or equal to b. If this is the definition of that contour, then the length is defined in this manner. So if this L is the length of that, and suppose that a function f of z is piecewise continuous on C, so there are some finite number of points on C at which this f need not be continuous, and this m is the non-negative value, that is the upper bound for the modulus of this function f of z for all points on C. That means the m is the upper bound for mod f of z for the values of f attains on C. Okay, and in that case, the modulus of this contour integral is always less than or equal to m times L. This m is the upper bound for that f, and this L is the length of the contour. So this upper bound for this contour integral is always less than or equal to the product of this upper bound of f mod f, that is m, and the length of the contour, that is the result. To prove this, we let z is equal to z of t. We need to evaluate an integral over a contour, so we put z is equal to z of t, a less than or equal to t less than or equal to b. Okay, so this is the parametric representation of C, that is, this is the definition of contour. And we know that integral over C f of z dz can be written as, to evaluate this integral, we use the parametric equation of the C. So that is integral a to b this is f of, we put z as z of t, we are evaluating f on the contour, and we put it as z dash t dt, and we need to evaluate the upper bound for this value, that means upper bound for this value. And if you observe the integrand of this, we can observe that this is a complex valued function defined on interval. So we can make use of the lemma what we have proved just before this theorem, that says that this is always less than or equal to integral a to b modulus of this f of z of t times modulus of z dash t dt. Okay, now what is this modulus stands for? We know that this f attains, z of t is a point on C, then f attains maximum of the value m. So we can take this, we can put the maximum value of this mod f of z of t, then we can write this is always less than or equal to integral a to b capital M times modulus z dash t dt. Okay, now you can take this m out from this integral, so this will be equal to m times integral a to b mod z dash t dt. But we know that this is the length of the contour, what we have defined in the section 39. So we write this is always equal to m times L. So we have this modulus is always, in modulus of this integral is always less than or equal to m times L. So this proves this theorem. And after that, some examples are discussed in the textbook, so please go through it. I'll illustrate one example here. Let's see be the arc of the circle mod z equal to 2, so that is a unit circle, in fact, center at 0, and we have this circle or center at 0, and it has radius 2, so this is 2, and we consider the part of the circle. We didn't take all of the circle, we take only the part of the circle from 2 to 2i. Okay, that means we delete all these points, we consider only the part of the circle lies on the first quadrant. So our contour will be like this. So from this, starting from this with this orientation, and this is our 2i. So this is the part of the circle, and we know that C takes the form, C is nothing but mod z equal to 2, and we can characterize this. Since this is a circle, we can easily find out what is L, what is the length of the circle. We know that the length of the circle is 2 pi r. Here r is again, I write r. Then this is the perimeter of all of the circle, and we need to take 1/4 of this length, because we need to consider only the part of the circle lies on the first quadrant. So we take it as L is equal to 2 pi r by 4, that is equal to 2 pi, but since the radius is 2, then this divided by 4, and we can write that is pi. So we have already shown that this modulus is always less than or equal to the length of C and the upper bound for this f of z. We already obtained what is L, length of C, so that is pi. Now we observe the upper bound for this f of z. We know that f of z is equal to z plus 4 divided by z cube minus 1. We know that z plus 4, the modulus of this is always less than or equal to mod z plus 4. Actually, this f is evaluated only on the contour. At the contour we have mod z equal to 2, therefore this is always 2 plus 4 equal to 6. That means the modulus of the numerator is always bounded by the 6. Now we write z cube minus 1. We know that this is always greater than or equal to mod z cube minus mod 1. this is because we know that a modulus of a minus b is always greater than or equal to mod a minus mod b. So using this fact, we can again write this mod z is always 2 on the circle or on the contour. We have 2 cube, that is 8. 8 minus 1 is equal to 7. That shows that this modulus is always greater than or equal to this. Then by taking the reciprocal of this, mod z cube minus 1 by mod z cube minus 1 is always less than or equal to 1 by 7. Now we multiply these two, 1 and 2. We will get modulus of z plus 4 times modulus of 1 by z cube minus 1. This is in fact, this is always less than or equal to 6 times 1 by 7, that is 6 by 7. This is in fact mod f of z. Okay, mod f of z is modulus of z plus 4 divided by modulus of z cube minus 1. So now we obtained the modulus or upper bound for f of z or mod f of z as well. So using these two quantities, this can be taken as L, M, and this can be taken as L. Now we have integral over C z plus 4 divided by z cube minus 1 dz. Modulus of this always less than or equal to m times L, which is equal to, what is m here? M is 6 by 7 and L is equal to 5. So this proves this problem. So there are a couple of examples are discussed after this, and exercise contains more than 2 or 3 problems with this type, so please go through it. And we after all, we can conclude this session with all of these examples and lemma and theorem.